In the early 1900s, spectral lines were precisely measured, yet classical physics and atomic theory offered two fundamentally different and incompatible explanations. A little-known physicist named Rudolf Ladenburg dared to rewrite the rules of optical dispersion using new quantum ideas and introduced one of the key ingredients of Heisenberg's matrix mechanics. This video is part of my series on the road to Heisenberg's matrix formulation of quantum mechanics. Make sure to check the previous videos for context. Last time, I presented the classical theory of dispersion in all its glory. From Newton to Cauchy, Sellmeier, Lorentz, and Drude, we found a microscopic interpretation of the refractive index, and, in passing, the Lorentz-Drude model gave us an explanation of the dark absorption lines in atomic spectra. But we also found a problem. After Bohr explained spectral lines as the consequence of quantum jumps, we were left with two successful but incompatible explanations. This is the formula that we found last time for the refractive index produced by a collection of electrons with a number density n, resonant frequency omega naught, and damping constant gamma. Experiments show that a material can have several resonant frequencies omega k, which are associated to different collection of electrons, each with number density nk and damping constant gamma k, so that the total refractive index is just the sum of all these groups of electrons that produce each observed resonance. Experiments also show that the damping constant is always very small, so it is common to simply write this reduced form. Many viewers ask me why our expression for the refractive index is n-1, while empirical formulas have n²-1 instead. The reason is that we used an approximation by only keeping the first terms of a Taylor series. I will name this big sum delta, which is a small quantity for most gases and materials that we will discuss. Note that n² can be approximated to leading order in delta as 1 plus 2 delta. In other words, we can write n²-1 as 2 times delta. So from now on, I will just use this. Today's protagonist is a little-known German physicist named Rudolf Ladenburg. After his doctorate under Wilhelm Röntgen in Munich, he moved to the University of Breslau, today part of Poland. Ladenburg was a distinguished experimentalist studying the photoelectric effect, but he was also a skilled theorist. During 1908, he began experiments about anomalous dispersion. Ladenburg and his assistant, the Polish experimentalist Stanislaw Loria, had the regular visit in the lab of two theorists, a former student of Max Planck named Fritz Reiche and a young mathematician named Max Born. Born was the local of the Breslau group. He was born and studied in Breslau until his classmate and close friend, the mathematician Otto Toeplitz, told him that he should go to Göttingen, where the leading mathematicians of the time were professors. Since students were allowed to move and take classes at different German universities, Bohr moved to Göttingen, where he found four of the most eminent mathematicians of the age: David Hilbert, Felix Klein, Hermann Minkowski, and Carl Runge. Although Bohr got his doctorate in mathematics with Runge, he was mostly trained by Hilbert, who offered him the appropriate space to develop as a physicist. After his doctorate, Bohr returned to Breslau. But after getting interested in special relativity, he received an invitation from Minkowski to join him back in Göttingen. Minkowski had developed a geometrical interpretation of Einstein's theory of special relativity, for which he had introduced the matrix representation of Lorentz transformations in spacetime. If you're not familiar with these terms, Lorentz transformations form the most basic mathematical principles underlying special relativity. Before moving to work with Minkowski, Bohr felt insecure about his linear algebra, and he knew that Minkowski required proficiency manipulating matrices and linear transformations. so his friend Toeplitz helped him refresh his matrix algebra. This minor episode will be extremely important when we decode Heisenberg's article in an upcoming video. Back in Breslau, Ladenburg and Loria set up a dedicated experiment combining an interferometer and a spectrometer to study spectral lines, anomalous dispersion, and more importantly, the relationship between their experimental results and the microstructure of the light-matter interactions. In particular, they developed a creative way to measure in hydrogen the number density of electrons responsible for the H-alpha absorption line. In October 1908, they found that in their experiment, dispersion was caused by 4 trillion electrons per cubic centimeter. They could measure the density of hydrogen in their apparatus with great accuracy. They found it to be 200 quadrillion atoms per cubic centimeter. This means that only 1 in 50,000 electrons participate in dispersion. Since not all electrons in the gas appear to participate, they call these active electrons dispersion electrons. But why such a small fraction? Why do only a few electrons resonate while the majority appear to be unaffected? This was a complete mystery that added to a similar feature reported the previous year by Ludwig Geiger in Göttingen, who found that in the process of magnetorotation of polarized light in sodium, only 1 in 200 electrons was active. Ladenburg considered this to be an important observation that could lead to a better understanding of the microscopic process. For the next 2 years, he and Loria attempted similar measurements in hydrogen lines at higher frequencies, but they could not determine the electron density with enough accuracy because H-beta and H-gamma lines are weaker than the H-alpha line. Nonetheless, from this observation, they inferred that the density of dispersion electrons should be even lower. While Ladenburg focused on hydrogen, Loria built an experiment to make the same measurements with sodium, which has a pair of absorption lines very close together, historically known as D1 and D2. In the spring of 1909, Loria reported the measurement of these densities of dispersion electrons for each line. He found a lower bound for the total number of sodium atoms, which leads to the ratios 1 in 200 for D1 and 3 in 400 for D2. With this, Loria confirmed Geiger's value, but also found 2 important results. Just like with hydrogen, the number density of dispersion electrons is a very small fraction of the total electrons available, and this number density of resonating electrons appears to decrease with the frequency of the spectral line. Meanwhile, Ladenburg improved his experiment and managed to measure the anomalous dispersion around the H-beta line, and found the fraction of dispersion electrons to be around 1 in 200,000, 4 times lower than the resonant electrons in H-alpha, confirming Loria's finding in sodium that the density of dispersion electrons decreases with the frequency of the spectral line. The following year in the UK, P.V. Bevan confirmed Ladenburg and Loria's discoveries in potassium vapors. Bevan explained the low number of dispersion electrons by temporary arrangements in the metallic vapor. On the contrary, Ladenburg was convinced that these differences were caused by some atomic property in the interactions with light. In the summer of 1913, Niels Bohr unveiled his quantum atomic model. Spectral lines were now understood as a consequence of quantum jumps between discrete electronic orbits around the nucleus. The experimental success of Bohr's model was great news for the understanding of atomic physics. But what about optical dispersion? What about the Lorentz-Drude model of resonating electrons? How could 2 completely different theories explain the same phenomenon so well? Ladenburg quickly accepted Bohr's model due to its early experimental success. However, this led to a problem. If absorption lines are generated by quantum jumps and not by a collection of dispersion electrons, what is the physical meaning of the density of electrons Nk in the dispersion formula? In other words, what on earth have he and Loria been measuring all these years? Part of Ladenburg's inspiration for solving this puzzle came after he was asked for a favor. At the University of Breslau, the senior experimentalists were Otto Lummer and Ernst Prinsheim, famous for their dedicated experiments on black-body radiation that guided Planck to his groundbreaking work in 1900. You might remember them from my first video on this series. During the time that Ladenburg was wondering about the meaning of dispersion electrons, Lummer asked him to support a talented doctoral student named Hedwig Kohn. In her doctoral thesis, Kohn thanks Ladenburg for his support in the lab. Their paths cross again 2 decades later, when together with Lise Meitner, Ladenburg helped Kohn to escape from Germany to the US. In late 1913, Kohn presented her thesis in which she experimentally confirmed that radiation emitted by incandescent bodies, such as metallic vapors, could be treated as thermal radiation. This result was highly influential for Ladenburg and inspired him to attempt using thermodynamics to model his dispersion electrons. In May 1914, Ladenburg published an article titled "On the Number of Atoms Involved in the Emission of Spectral Lines," in which he proposed a way to characterize the number of dispersion electrons. Unfortunately, I was not able to find a copy of this article. I found a copy of the journal, but the pages with Ladenburg's article were missing. I only know the final result, so here I decided to attempt to reproduce Ladenburg's train of thought. The goal is to characterize the amount of energy emitted by the dispersion electrons per unit volume and time. This quantity is called a current density. The first step is to find the energy of a single, one-dimensional resonating electron, which is in general given by this expression. I am calling the energy U to avoid confusion with the electric field. From the previous video, you will remember that we solved the equation of motion of electrons in the material and found that their position is the real part of this long expression. At the resonant frequency omega naught, this reduces to a simple sinusoidal function, where the overall factor represents the amplitude of the oscillation that I will simply denote by A. From here, we can directly take the first and second time derivatives that will be needed later, so I will keep them up here. Now we can replace the speed and position in the energy formula and collect common factors. Note that the Pythagorean theorem implies that the term in parentheses is equal to 1, and the energy takes this simple form. I will need this in a minute. Now we calculate the radiated power emitted by a resonant electron using the famous Larmor formula. Plugging the acceleration found before, we get an expression that depends on the amplitude A. Here we use the energy relation to eliminate A and simplify terms. This is the power radiated as a function of time. Now we can calculate the average power radiated during a full cycle of the electron's oscillation. All the constant terms remain unchanged and only the sine square omega t is averaged. It can be shown that this average is always 1/2, and the average radiated power becomes this, where I am now using frequency instead of angular frequency. And with this quantity, we can finally define the classical current density as the total energy radiated per unit volume and time, which for n electrons per unit volume is 3n times the average radiated power. The number 3 is there because each electron can vibrate in 3 dimensions. Plugging our last result, we get this expression. Almost there. The last step is a result used by Planck, in which the energy density of the blackbody radiation can be written as this overall factor times the energy of the system, U. Solving for U, we get this, which can be replaced in our expression of the current density. After simplifying common factors, we get our final result. This is the result that Ladenburg found for the classical current density. His plan was to calculate an equivalent quantum current density to finally resolve the mystery of the quantum meaning of the n dispersion electrons. However, he didn't know how to do it, and World War I interrupted his work. Ladenburg was sent to the front, but soon relocated to a unit in Berlin, researching methods for determining the location of enemy artillery. In Berlin, he found an active physics community, including Einstein, Walter Nernst, Heinrich Rubens, and Fritz Haber. Max Born was also sent to the front, but discharged due to an acute asthma condition. He was also sent to Berlin, where he joined his old friend from Breslau. This would not be the last time that a respiratory condition helped in the development of quantum mechanics. During the wartime, the conflict between the classical Lorentz-Drude model and the quantum Bohr model was not ignored. According to Bohr's quantum rule, electrons are confined to orbit the nucleus in precise orbits. Then how could they also vibrate, leading to the resonances required by the Lorentz-Drude model? Any radial vibration was excluded because it would violate the key principle of an electron only allowed to move at a specific radius. But what about oscillations perpendicular to the orbital plane? Bohr already considered this possibility in part 1 of the trilogy, but it was Arnold Sommerfeld, and independently his former student Peter Debye, who explored this type of motion during 1915. Debye and Sommerfeld defended the idea that even though spectral lines have a quantum origin, dispersion was a purely classical phenomenon. They developed a classical theory for optical dispersion, in which electrons could oscillate around their stationary Bohr orbits, leading to a motion equivalent to the Lorentz-Drude description of dispersion. Additionally, electrons could also perform quantum jumps between the discrete orbits of Bohr's model. I personally find this surprising because both Sommerfeld and Debye were strong supporters of quantum descriptions of light-matter interactions, but for dispersion, somehow they found a fully classical approach more compelling. Bohr was completely against the Debye-Sommerfeld model, and many letters and articles of the time show that this model was not very popular. Dutch physicist Hendrika van Leeuwen was a renowned student of Lorentz that demonstrated in her doctoral thesis presented in 1919 that magnetism could not be explained only using classical physics. She proved that magnetism must be a purely quantum phenomenon, a result known today as the Bohr-van Leeuwen theorem. But she was still a doctoral student in April 1916 when she demonstrated that the Debye-Sommerfeld model implied that, contrary to observations, the hydrogen molecule would be unstable. Another important flaw of the Debye-Sommerfeld model was that it only worked if the resonance and absorption frequencies were different, also in contradiction with observations. For decades, experiments showed that the frequency of absorption lines coincide with the resonant frequency that produced the anomalous dispersion. Sommerfeld defended the model for a few years, but in light of the conceptual and experimental arguments against it, he accepted that his model could not be correct. After the war, Ladenburg returned to Breslau, and quantum physics became his main interest. His first post-war article on quantum physics was a review of the existing literature on the theoretical and experimental properties of chemical elements, followed by an article collecting all experimental methods for estimating Planck's constant. The breakthrough came with his third article. Published in February 1921, this was not an article about dispersion, but about the quantum meaning of the density of dispersion electrons. Contrary to his 1914 article, now Ladenburg found a procedure to calculate the quantum current density in Einstein's groundbreaking article on quantum radiation. In retrospect, Ladenburg's advance is quite straightforward. He used his classical result from 1914 and now calculated the quantum current density, then forced them to be equal, from where he found a quantum interpretation for the dispersion electrons. Let me show you the details. Ladenburg wrote the quantum current density as the product of the transition energy and the corresponding transition rate. If you watch my video about atomic transitions, you will remember that Einstein introduced the transition probabilities, also known as A and B coefficients. For emission of light, the current density becomes the energy h nu times the rate for spontaneous and stimulated emission, where J and K denote the two energy levels of the transition. In equilibrium, the rate of emission is equal to minus the rate of absorption, which is easier to calculate, so this is what Ladenburg used. Also in the previous video, I showed you that the A and B coefficients are related in this way. Combining these two relations, we can write the absorption coefficient BKJ in terms of the spontaneous emission coefficient AJK. Plugging this back in the current density and eliminating the minus sign by reverting the indices of the frequency nu, we get this result. Now comes the bizarre step. Bringing back his result for the classical current density, Ladenburg set them to be equal. I know this might not look like much, but think about it. He is literally forcing the result of two incompatible theories to be equal. Similarly, he was forced to respectively identify the resonance frequency nu0 and the energy density ρ0 with the transition frequency nu kj and the energy density ρ kj. Although he only added a footnote about this step is highly non-trivial, because both mechanisms, resonance and quantum jumps, are conceptually incompatible. However, Ladenburg made this choice guided by observations. All experiments confirm that the resonant frequencies producing anomalous dispersion coincide with the frequencies of spectral lines. This is the step that made Ladenburg's approach a success where Debye and Sommerfeld failed. Simplifying this relation produces the final result, a formula relating the number density of dispersion electrons of the classical Lorentz-Drude model with the quantum quantities of Bohr's atomic model and Einstein's transition probabilities. This is Ladenburg's way of writing Bohr's correspondence principle, which relates quantum quantities to their corresponding classical counterparts. Note that this result is not supposed to be an equation to be solved. For Ladenburg, the left-hand side is a purely classical quantity, and more importantly, something to be measured in the lab, while the right-hand side is what has a quantum meaning. He explicitly wrote, "The left side of this equation can be looked upon as the definition for the experimentally determinable quantity n, which has, of course, no definite meaning in quantum theory." This relation also shows that the density of dispersion electrons decreases with the transition frequency, which explains the observations by Loria in sodium and Ladenburg in hydrogen. Seen the other way around, this formula allows the experimental exploration of Einstein's quantum transition probabilities. The rest of Ladenburg's article is a collection of experimental results in atomic physics and their interpretation using his newly found formula. Ladenburg took the first step connecting the classical and quantum worlds. Guided by experiments on anomalous dispersion, he made use of recent developments and found a formula that would be heavily exploited in the following years. Ladenburg did not explicitly mention it, but his formula also hides one of the key ingredients of Heisenberg's matrix mechanics. You might have noticed that the left-hand side is just the number n, whereas indices j and k are all over the place on the right-hand side. This is always a sign that a careful inspection is needed. In the next part, I will show you that, indeed, a more rigorous treatment reveals that Ladenburg's formula conceals a collection of mathematical objects that Alfred Landé later called the virtual orchestra.